This is Chapter 7, Teach the Dog. So the first question, the first part is that we're supposed to classify the following bonds as polar or nonpolar. On the polar bonds, we use the two symbols that indicate the polarity of the bonds, and we explain. Explanation for the different bonds is that it depends on electronegativity difference. Nonpolar means that there is an equal sharing of electrons by atoms, and polar means an unequal sharing of electron by atoms. If the difference in electronegativity between atoms is less than 0.4, then it's nonpolar. So that's just an important fact to know when we're going into doing this. So I'm going to write down the equations real quick, or bonds I mean, and show them to you. So the first one is fluorine. Make sure I'm saying the right names. Fluorine and chlorine. And fluorine is the more negative one, so it gets the S minus, because I'm not sure what you actually call that. I can't remember off the top of my head. And the other one gets the S positive. Because fluorine's electronegativity number is 4.0, chlorine's is 3.0. That means the difference between them, and I put that underneath the dash, is 1.0. That number makes this a polar bond. Fluorine to chlorine, the difference in electronegativity is 1.0, making it a polar bond, because it is greater than 0.4, with chlorine being the less electronegative atom. On the next one, we have carbon and sulfur. They are both 2.5 on the electronegativity scale. And again, I put my difference underneath the dash. So there is no difference in electronegativity, making them non-polar. It is a non-polar bond. They equally share the electrons between them. The next one is hydrogen and bromine. And hydrogen is 2.1, bromine is 2.8. So the difference is 0.7, and that makes it polar. Hydrogen is obviously going to be the less electronegative atom, with bromine being the more. So I have marked which one of them gets the correct symbol on the top. And since the difference is 0.7, they are polar. And the next one is boron and hydrogen. And they are 2.0 on boron and 2.1 on hydrogen. That makes the difference only 0.1, which makes it a non-polar bond. Boron, hydrogen. Difference is 0.1, non-polar. And the last one for this section is chlorine and sulfur. Chlorine is the less electronegative, or the more electronegative, I'm sorry, I said that wrong. Sulfur is the less, so I put the minus and plus electronegativity on them. Chlorine is 3.0, sulfur is 2.5. That makes the difference 0.5. They are just over nonpolar, making it into a polar bond. And I have that all written out right there. 0.5 equals polar. Chlorine is the more electronegative atom. All right, so now we're going to move on to the second section of this assignment. we have to draw Lewis structures for CO2 and H2O, showing the correct bond angles, and indicate the direction of polarity on the bonds on each molecule, which molecule is polar, and explain the choice. So the first thing I do here is C is 2.5. Wait, no, the first thing I have to do is the Lewis structure stuff. So C is 4 valence electrons times 1 carbon atom equals 4. Oxygen is 6 valence electrons times 2 oxygen atoms equals 12. That gives me 6 valence electrons that I have to distribute. So I then write the equation O dash C dash O. And then the next step here is figuring out my Lewis structure. So I'm going to make, I already have 4 valence electrons because of the dashes between O and C on both sides. So that gives me 4. So now I'm going to start adding my electrons on both sides. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now I have all 16 valence electrons. I'm going to actually drop 2 of these electrons to share between C and O so that I give the C a full octet. So it's going to end up O dash dash C, double bond again, O, with 2 lone pairs on both of the oxygen atoms on the ends. The next thing is that O's electric negativity is 3.5, carbon's is 2.5. So the least electronegative is pointed outward. So we are going from least to most. So carbon is least, so we draw the line away from carbon to the outside, and we do that on both sides. I'm going to actually separate my Lewis structures more because I think I'm making it a little confusing with how close I'm putting them together. So O dash dash C dash dash O dot 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 dot, and then line and line. So you can see that I have the electronegative going from carbon to oxygen, and because both of them are pointing out, they actually will cancel each other out. And because they cancel each other out, there is no net dipole moment, and that makes carbon dioxide, CO2, a non-polar. So that molecule is non-polar. All right, so the next one I'm going to do is H2O. H2O. H has 1 valence electron times 2 atoms. O has 6 valence electron times 1 atom. So we have 2 electrons from H and 6 electrons from oxygen, giving us 8 valence electron to distribute. 8 valence electrons. So my Lewis structure here is H dash O dash H. You cannot put any lone structures on H because H can only have one electron, and that is the one that is connected to the bond it shares with oxygen. So we put the remaining valence electrons, of which there are 4, giving oxygen 2 lone pairs attached to it with 2 chemical bonds. So this is the Lewis structure up here for water. Now we are going to know that H, hydrogen, electronegativity is 2.1. Oxygen's electronegativity is 3.5. So the electronegativity on this will point inward towards oxygen, the more electronegative of the atoms. So there will be a dipole moment, which means that it is a polar. It's a polar molecule, and that there are unshared electrons on the central molecule because we cannot share those with hydrogen. So there is, oh, I forgot to put my dots on my O. So there's that. But, oh, I forgot one thing. On carbon dioxide, CO2, I forgot to show the correct bond angle. It's a linear, so the bond angle is 180 degrees, just in case I didn't mention that, and I don't think I did. So on water, we actually have one more step, and that is putting this in the correct, showing the correct bond angle. So H, O, dash, and there we go. So water is, and then the bond angle is down between the 2 hydrogen atoms, and that bond angle is less than 109 degrees. So there is that equation. And that is also my next one. Give one example of a polar linear molecule and how it's different from carbon dioxide. Well, my example is water, and it's different because it's polar. It has a net dipole moment, which is present. It's involved in hydrogen bonding. It has a positive partial and positive negative and partial negative charges in the bond. So that answers the next part. And now we're going to move on to the next page where we completed this chart. So it wanted to know for group 1A, we were given the element lithium, and it has 1 valence electron, and its Lewis dot structure is Li with 1 dot. There's a lithium, 1 valence electron, which I'm going to just do V dot E dot from now on instead of writing it out. And the next one is beryllium, Be, I believe I said that right. Yes, beryllium. And it has 2 valence electrons. and its Lewis dot structure is B, and it has 2 dots. BE with 2 dots, one on each side of it. So we have boron is the next one on the table. It has 3 valence electrons, and boron has 3 valence electrons, and I have the dots around the B. Carbon has 4 valence electrons, 2 dots on 2 sides. Nitrogen has 5 valence electrons, 2 dots on 2 sides, 1 dot on 1 side. So, and the next one is oxygen, and it has 6 valence electrons, and we have 2 dots on both sides and 3 dots on 3 sides. 2 dots on 3 sides. The next one is fluorine, and it has 7 valence electrons, and fluorine gets dots on every side, but one side only has a 1 dot. Lastly, we have neon with 8 valence electrons. So it has a complete octet, and for some reason I wrote the number 8 instead of neon for that. Let's fix that. Ne dot 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 dot. So it has the complete, got all of its bonds met from its own valence electrons. Okay. All right, so I am given 3 molecules and polyatomic ions. I am supposed to show how many valence electrons are present in each of the following substances, along with the Lewis structure. So we start with SCl2. Sulfur has 6 valence electrons times 1 atom equals 6 valence electrons for sulfur. Chlorine has 7 valence electrons times 2 chlorine atoms equals 14 valence electrons. You add those together, we have 20 valence electrons available for our Lewis dot structure. So we're going to start out with Cl dash S dash Cl. So that is the basic structure we're beginning with. Now we're going to start adding the valence electrons around our ends. So we already have 4 valence electrons, so we have 16 left to place. So 6, 8, 10, 12, 14, 16. So we still have 4 valence electrons, but both atoms on the end are done. So we're going to add those 4 to sulfur, giving it 2 lone pairs and 2 chemical bonds to complete its octet. So this is what it looks like. But we can go a step further and make that a double bond between sulfur and chlorine on both sides by distributing those lone pairs. So that gives us Cl, double bond, S, double bond, Cl. So 20 valence electrons. Woo with structure. Okay, let's go on to the next one, HCN. HCN. H, we have 1 valence electron times 1 atom equals 1 valence electron. Carbon, we have 4 valence electrons times 1 atom equaling 4 valence electrons. Nitrogen, we have 5 valence electrons times 1 atom equaling 5 valence electrons. 1 plus 4 plus 5 equals 10 valence electrons. Now, the hydrogen can only have the dash from it to C. And we are going to then do 1 dash to the N. That gives us 4 electrons. We're going to take the rest of those 6 and put them around nitrogen. Now, if we wanted to make it so that carbon had, could try and complete it, we could make it a triple bond, I think. This is where I get a little confused, but I think it could be I think it could be this. So 10 valence electrons, H dash, H single bond, C triple bond, N with a lone pair of electrons on nitrogen. And the last one for this page is SO4 with a -2 charge. So we'll have brackets involved and 2 extra electrons. So S has 6 valence electrons, 1 atom equaling 6 valence electrons. Oxygen has 6 valence electrons times 4 atoms equaling 24 valence electrons. Because the charge is -2, we add 2 electrons. So we end up with 32 valence electrons on this problem. So I'm going to draw my brackets, put my 2 negative charge. I'm going to put my S in the middle with a dash coming out on all sides, 2 oxygen atoms. There's a single bond connected to each oxygen atom. There's all that work so far. Now I have, because that only gives me 8 valence electrons so far, so I have 24 left to go. So 24 divided by 4 is 6, so each oxygen atom gets 3 lone pairs to equal 6 valence electrons on each one. So there's that. So I have 6, 12, 18, 24, 26, 28, 30, 32. I think we could take 1 lone pair from each oxygen atom and put it and make double bonds for oxygen to sulfur to give the sulfur the complete 8 bonds or 8 electrons. So I believe that this could be what it looks like in the end. That's the part I'm kind of struggling with, because sometimes it looks like you complete it like that and some it doesn't. So I don't know if I'm going a step too far for this part or not. The next page, I'll just read this one. The formal charge on an atom equals the number of valence shell electrons minus the number of lone pair electrons plus half the number of bonding electrons. Okay. The next one asks me to calculate the formal charge on each atom for carbon monoxide, CO. So I'll just do this out real quick. CO. And we have C has 4 valence electrons minus, okay, now I got to do my Lewis dot structure before I can move on to that second part. But we can do the valence electrons for both of these real quick so that we have the first part we need done for the equation already. So carbon has 4 valence electrons and oxygen has 6 valence electrons, and we will minus it from the second number we're going to find. So we have to do our Lewis dot structure. So C dash O, and when you add the 2 valence electrons together, we get 10. So we already have 2 in the middle, so that leaves us with 8, giving us 2 on each end. And to make it share as much as possible, we are going to transfer a lone pair from each atom to make it a triple bond between them. So what this becomes is C triple bond to O, with both of them retaining lone pairs. So that gives us 5 electrons on carbon and 5 electrons on oxygen. So you take the number of lone pair electrons and half the number of bonding electrons. So they have 6 bonding electrons, but you divide that in half, making it 3. And then I add my 2 lone pair electrons, making it 5, because they share all of them. So 4 minus 5 for carbon gives me a -1 formal charge. 6 minus 5 on oxygen makes it a +1 formal charge. So carbon has a -1, oxygen has a +1, and that is my formal charge for that atom. All right. We now have another table, and the first thing is we have the element H2O again, which I've already gone over. It wants to know the Lewis dot structure the Vespert shape and how many lone pairs we have on the central atom. Well, it's a hydrogen bond, so there is just one bond, chemical bond between the hydrogen atoms and the oxygen atom. Hydrogen has one valence electron times 2 atoms, giving us 2. Oxygen has 6 valence electrons times 1 atom, giving us 6. That gives us 8 valence electrons total, with 4 of them going to the chemical bonds between the hydrogen atoms and the oxygen. We have 2 lone pairs to put on oxygen to make up our 8 electrons for our Lewis structure. So there are 2 lone pairs on H2O, and the shape is linear. So that is the answer for that. We have BF3. I believe that's boron trifluoride. I'm sorry, I don't know those by heart. Okay, so boron goes in the middle. We have a fluorine compound atom coming out on each side. Boron has, I didn't write that part down here. Where do I have that? Okay, so boron has 3 valence electrons times 1 atom, giving it 3 total. Fluorine has 7 times 3 atoms, giving it 21 valence electrons total. When you add 3 and 21, you get 24 valence electrons total. Okay, we already have 6 distributed between the boron atom and the fluorine atoms. So that leaves us with 18 to distribute. So we will put those 6 dots all around and there is boron with fluorine atoms surrounding it. We don't have any valence electrons left because 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. They are all used up on the surrounding atoms. So it would be 3 chemical bonds on the central atom, but no lone pairs. So the answer is no lone pairs. I think you could take 2 of those lone pairs from 2 of the fluorine atoms and give it triple bonds to fill out. And then on the top one, you could take 1. So I think that to make the boron complete, it would look like this. Because that would give boron 8 electrons in the middle, but there would still be lone pairs. Oh, I didn't move it far enough there. But there would still be lone pairs in the fluorine atoms. I think you could do that. Okay, and then, oh, where did my sheet go? That gives us a, I don't know if I'm saying this right, trigonal planar shape. All right, so we're going to move on to the next example on the table and complete it. XeF4. So the first thing we do is find out how many valence electrons the equation calls for. So Xe has 8 valence electrons times 1 atom is 8 valence electrons total. Fluorine has 7 valence electrons times 4 fluorine atoms equals 28 valence electrons total. 28 plus 8 is 36 valence electrons to work with. So we are going to put the Xe in the middle, and we are going to put fluorine atoms all around it. We've already used up 8 valence electrons. We are going to now do valence electrons around fluorine until we have used up all the spots, or we've used up all the 28 remaining valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we still have 4 electrons remaining. Which means we are going to put those 2 lone pairs on the central atom. So that is what that looks like. 2 lone pairs have to go on the central atom. So what's going to happen is I believe that will give us double bonds now for each fluorine atom. And we still have one side on each fluorine atom that only has 1 electron. And the shape is tetrahedral. Tetrahedral. Okay, the next example on this table is PCl5. PCl5. First, we start with our valence electrons. Phosphate has 5 times 1 atom equals 5 valence electrons. Chlorine has 7 times 5 equals 35 valence electrons. You add that together, giving yourself 40 valence electrons on this. So phosphate is going to go in the middle, and we are going to have 5 single bonds coming off of it, connecting to chlorine. So that gives us 10 valence electrons already used in our single bonds connecting all of the atoms. So that leaves us with 30 valence electrons to divide between the 5. So each one of those will have 3 lone pairs. And that will satisfy. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So it is all around. However, the phosphate ion still only has 5 electrons on it. So 3 of these could become double bonds, I believe. So All right. Down here shows that phosphate now has 8 electrons. So it has 5 chemical bonds and no lone pairs. Did I say there was lone pairs on XCF4? Okay, yeah, there was originally, but when we moved them away, there was none. So it just depends on which equation or which structure is correct. So no matter what here, there were 0 lone pairs on the central atom phosphate. And because it has 5 regions, it is a trigonal bipyramid. Zero lone pairs makes it a trigonal, and 5 regions makes it a trigonal bipyramid. All right, we have SF6 to do for our last example. Sulfur. So, sulfur has, where's that little piece of paper? Sulfur has 6 valence electrons times 1 atom equals 6 valence electrons. Fluorine has 7 valence electrons times 6 atoms equals 42 valence electrons. You're going to add that together and you get 48 valence electrons. So we are going to put sulfur in the middle and we are going to draw single bonds to all 6 fluorine atoms that surround our central atom, sulfur. So 5 single bonds times 2 electrons makes it 10 electrons being used up right there. That leaves us with 38. So 6 times 6 is 36. So we're going to have 2 lone pairs on sulfur. I'm sorry, 1 lone pair, 2 electrons left on sulfur. So there's the next step on my Lewis structure. 2 of these bonds on sulfur are going to become double bonds. Giving sulfur 8 total electrons to complete its octet. So in the end, the question is which one we start from. So it could be that there's 1 lone pair or 0. I went with 0, meaning that my shape is octahedral. I'm hoping that my understanding was correct and I did these right. Okay, and the last page of our documents. So we have to fill out this chart on molecular geometry. We have to say what the number of bonding groups on the electrons was, number of bonding groups of electrons, the number of lone pairs of electrons, the shape, and then the example is given to us and the number of electron density region groups was given to us. So it's pretty simple here. CO2 is the example. It has two regions of electron density with the two double bonds that it shares with oxygen. So it gives us two electron density groups, no lone pairs of electrons on carbon, four bonding groups of electrons, and it is a linear shape. Just to show you my work. Okay. BCl3 is trigonal planar, no lone pair on boron, so that's 0. There were three bonding groups of electrons because of the chemical bonds on boron and chlorine together, holding them together. So, and there were only 3 electron density. Okay, so the next one is NH4+. That's a tetrahedral shape. There are no lone pairs left for nitrogen. Because nitrogen has 5, yeah, it would just be a single, and that's taken away from the positive sign there. So yeah, it's 0 lone pair. There are 4 bonding groups of electrons because of the chemical bonds between nitrogen and hydrogen on all sides. Tetrahedral shape. The next equation it's still 4 electron density groups for water, H2O. It does have 2 lone pairs on oxygen and only 2 chemical bonds because of hydrogen only allowing 1 chemical bond each. And it's a tetrahedral bent shape. 5 electron density groups, 4 bonding groups of electrons, 1 lone pair on the central atom, sulfur. Trigonal bipyramid seesaw, that's for SF4. 6 areas of electron density on XeI4 because there are 2 lone pairs and 4 chemical bonds. So number of bonding groups of electrons, 4. Number of lone pairs of electrons, 2. Octahedral square planar, or planar, however you say that. And that was a very long teach the doc, but it is done. And end stream.